25,002 operations to create a new version of the list. Joe, correct. Theo, let's split the list again then. Joe, absolutely. In fact, we can split the list again and again until the size of the list is at most 2. Can you guess what is the complexity of creating a new version then? Theo, I'd say around log 2 n operations. Joe, I see that you remember well your material from school. Do you have a gut feeling about what is log 2 n when n is 100,000? Theo, let me see. 2 to the power of 10 is around 1,000, and 2 to the power of 7 is 128, so it should be a bit less than 17. Joe, it's 16.6 to be precise. It means that in order to update an element in a persistent list of 100,000 elements, we need around 17 operations. The same goes for accessing elements. Theo, nice, but 17 is still not negligible. Joe, I agree. We can easily improve the performance of accessing elements by using a higher branching factor in our tree. Theo, what do you mean? Joe, instead of splitting by 2 at each level, we could split by 32. Theo, but the running time of our algorithm would still grow with log n. Joe, you're right. From a theoretical perspective, it's the same. From a practical perspective, however, it makes a big difference. Theo, why? Joe, because log 32n is 5 times lower than log 2n. Theo, that's true. 2 to the power of 5 is 32. Joe, back to our list of 100,000 elements. Can you tell me how many operations are required to access an element if the branching factor is 32? Theo, with a branching factor of 2, it was 16.6. If I divide 16.6 by 5, I get 3.3. Joe, correct. Tip. By using a branching factor of 32, we make elements accessed in persistent lists more efficient. Theo, does this trick also improve the performance of updating an element in a list? Joe, yes, indeed it does. Theo, how? We'd have to copy 32 elements at each level instead of 2 elements. It's a 16 times performance hit that's not compensated for by the fact that the tree depth is reduced by 5 times. Joe, I see that you are quite sharp with numbers. There is another thing to take into consideration in our practical analysis of the performance: modern CPU architecture. Theo, interesting. The more you tell me about persistent data structures, the more I understand why you wanted to have this session at a university. It's because we're dealing with all this academic stuff. Joe, yep. So, to continue, modern CPUs read and write data from and to the main memory in units of cache lines, often 32 or 64 bytes long. Theo, what difference does that make? Joe, a nice consequence of this data access pattern is that copying an array of size 32 is much faster than copying 16 arrays of size 2 that belong to different levels of the tree. Theo, why is that? Joe, the reason is that copying an array of size 32 can be done in a single pair of cache accesses, one for read and one for write, although for arrays that belong to different tree levels, each array requires its own pair of cache accesses, even if there are only 2 elements in the array. Theo, in other words, the performance of updating a persistent list is dominated by the depth of the tree. Tip. In modern CPU architectures, the performance of updating a persistent list is dominated much more by the depth of the tree than by the number of nodes at each level of the tree. Joe, that's correct, up to a certain point. With today's CPUs, using a branching factor of 64 would, in fact, decrease the performance of update operations. Theo, I see. Joe, now I'm going to make another interesting claim that is not accurate from a theoretical perspective, but accurate in practice. Theo, what is it? Joe, the number of operations it takes to get or update an element in a persistent list with branching factor 32 is constant. Theo, How can that be? You just made the point that the number of operations is log 32n. Joe, be patient, my friend. What is the highest number of elements that you can have in a list in practice? Theo, I don't know. I never thought about that. Joe, let's assume that it takes 4 bytes to store an element in a list. Theo, okay. Joe, now can you tell me how much memory it would take to hold a list with 10 billion elements? Theo, you mean one with 10 zeros? Joe, yes. Theo, each element takes 4 bytes, so it would be around 40 gigabytes. Joe, correct. Do you agree that it doesn't make sense to hold a list that takes 40 gigabytes of memory? Theo, I agree. Joe, so let's take 10 billion as an upper bound to the number of elements in a list. What is log 32 of 10 billion? Once again, Theo uses the blackboard to clarify his thoughts. With that, he quickly finds the answer. Theo, 1 billion is approximately 2 to the power of 30. Therefore, 10 billion is around 2 to the power of 33. That means that log 2 of 10 billion is 33, so log 32 of 10 billion should be around 33 divided by 5, which is a bit less than 7. Joe, I am impressed again by your sharpness with numbers. To be precise, log 32 of 10 billion is 6.64. Theo, smiling, I didn't get that far. Joe, did I convince you that in practice, accessing or updating an element in a persistent list is essentially constant? Theo, yes, and I find it quite amazing. Tip. Persistent lists can be manipulated in near constant time. Joe, me too. Theo, what about persistent maps? Joe, it's quite similar, but I don't think we have time to discuss it now. Startled, Theo looks at his watch. This morning's session has gone by so quickly. He notices that it's time to get back to the office and have lunch. Section 9.3. Persistent Data Structures Libraries. On their way back to the office, Theo and Joe don't talk too much. Theo's thoughts take him back to what he learned in the university classroom. He feels a lot of respect for Phil Bagwell, who discovered how to manipulate persistent data structures efficiently, and for Rich Hickey, who created a programming language incorporating that discovery as a core feature and making it available to the world. Immediately after lunch, Theo asks Joe to show him what it looks like to manipulate persistent data structures for real in a programming language. Theo, are persistent data structures available in all programming languages? Joe, a few programming languages like Clojure, Scala, and C# provide them as part of the language. In most programming languages, though, you need a third-party library. Theo, could you give me a few references? Joe, sure. Using Theo's laptop, Joe bookmarks some sites. He knows exactly which URLs to look for. Then, while Theo is looking over the bookmarked sites, Joe goes to the whiteboard and jots down the specific libraries in Table 9.1. Immutable.js for JavaScript at immutable-js.com. Paguro for Java at github.com/GlennKPeterson/Paguro. Immutable collections for C# at mng.bz/qw51. Persistent for Python at github.com/tobgu/pyrsistent. Hamster for Ruby at github.com/hamstergem/hamster. Theo, what does it take to integrate persistent data structures provided by a third-party library into your code? Section 9.3.1. Persistent Data Structures in Java. Joe, in an object-oriented language like Java, it's quite straightforward to integrate persistent data structures in a program because persistent data structures implement collection interfaces, besides the parts of the interface that mutate in place. Theo, what do you mean? Joe, take for instance Paguro for Java. Paguro persistent maps implement the read-only methods of java. java.util.map, like get and contains key, but not methods like put and remove. On the other hand, Paguro vectors implement the read-only methods of java.util.list, like get and size, but not methods like set. Theo, what happens when we call put or remove on a Paguro map? Joe, it throws an unsupported operation exception. Theo, what about iterating over the elements of a Paguro collection with a for each? Joe, that works like it would in any Java collection. Here, let me show you an example. Theo, what about Java streams? Joe, Paguro collections are Java collections, so they support the Java stream interface. Take a look at this code. Tip: Paguro collections implement the read-only parts of Java collection interfaces. Therefore, they can be passed to any methods that expect to receive a Java collection without mutating it. Theo, so far you told me how to use Paguro collections as Java read-only collections. How do I make modifications to Paguro persistent data structures? Joe, in a way similar to the _.set function of low-fp that we talked about earlier. Instead of mutating in place, you create a new version. Theo, what methods does Paguro expose for creating new versions of a data structure? Joe, for vectors you use replace, and for maps you use ASSOC. Theo, yes, now I see how to use persistent data structures in Java, but what about JavaScript? Section 9.3.2, Persistent Data Structures in JavaScript. Joe, in a language like JavaScript, it's a bit more cumbersome to integrate persistent data structures. Theo, how so? Joe, because JavaScript objects and arrays don't expose any interface. Theo, bummer. Joe, it's not as terrible as it sounds, because immutable.js exposes its own set of functions to manipulate its data structures. Theo, what do you mean? Joe, I'll show you in a moment, but first, let me show you how to initiate immutable.js persistent data structures. Theo, okay. Joe, immutable.js provides a handy function that recursively converts a native data object to an immutable one. It's called immutable.fromJS. Theo, what do you mean by recursively? Joe, consider the map that holds library data from our library management system. It has values that are themselves maps. Immutable.fromJS converts the nested maps into immutable maps. Theo, could you show me some code? Joe, absolutely. Take a look at this JavaScript code for library data. Theo, do you mean that the catalog value in library data map is itself an immutable map? Joe, yes, and the same for books by ISBN, author IDs, and so forth. Theo, cool. So how do I access a field inside an immutable map? Joe, as I told you, immutable.js provides its own API for data access. For instance, in order to access a field inside an immutable map, you use immutable.get or immutable.getin, like the following. Theo, how do I make a modification to a map? Joe, similar to what we did with low-fp, you use an immutable.set or immutable.setin map to create a new version of the map where a field is modified. Here's how. Theo, what happens when I try to access a field in the map using JavaScript's dot or bracket notation? Joe, you access the internal representation of the map instead of accessing a map field. Theo, does that mean that we can't pass data from immutable.js to Lodash for data manipulation? Joe, yes, but it's quite easy to convert any immutable collection into a native JavaScript object back and forth. Theo, how? Joe, immutable.js provides a toJS method to convert an arbitrary deeply nested immutable collection into a JavaScript object. Theo, but if I have a huge collection, it could take lots of time to convert it, right? Joe, true. We need a better solution. Hopefully, immutable.js provides its own set of data manipulation functions like map, filter, and reduce. Theo, what if I need more data manipulation, like low-dashes _group by? Joe, you could write your own data manipulation functions that work with the immutable.js collections, or use a library like mudash, which provides a port of low-dash to immutable.js. Note: you can access the mudash library at github.com/brianneisler/mudash. Theo, what would you advise? Joe, a cup of coffee. Then I'll show you how to port functions from low-dash to immutable.js and how to adapt the code from your library management system. You can decide on whichever approach works best for your current project. Section 9.4. Persistent Data Structures in Action. Joe, let's start with our search query. Can you look at the current code and tell me the low-dash functions that we used to implement the search query? Theo, including the code for the unit tests? Joe, of course. Note: see Chapter 6 for the unit test of the search query. Section 9.4.1. Writing queries with persistent data structures. Theo, the low-dash functions we used were get, map, filter, and isEqual. Joe, here's the port of those 4 functions from low-dash to immutable.js. Theo, the code seems quite simple, but can you explain it to me, function by function? Joe, sure. Let's start with get. For accessing a field in a map, immutable.js provides 2 functions, get for direct fields and getIn for nested fields. It's different from low-dash, where _.get works both on direct and nested fields. Theo, what about map? Joe, immutable.js provides its own map function. The only difference is that it is a method of the collection, but it is something that we can easily adapt. Theo, what about filter? How would you make it work both for arrays and maps like low-dash's filter? Joe, immutable.js provides a value seq method that returns the values of a map. Theo, cool. And what about isEqual to compare 2 collections? Joe, that's easy. Immutable.js provides a function named is that works exactly as isEqual. Theo, so far so good. What do I need to do now to make the code of the search query work with immutable.js? Joe, you simply replace each occurrence of an underscore with immutable. Underscore.map becomes immutable.map. Underscore.filter becomes immutable.filter. And underscore.isEqual becomes immutable.isEqual. Theo, I can't believe it's so easy. Joe, try it yourself. You'll see. Sometimes it's a bit more cumbersome because you need to convert the JavaScript objects to immutable.js objects using immutable.fromJS. Theo copies and pastes the snippets for the code and the unit tests of the search query. Then he uses his IDE to replace the underscore with immutable. When Theo executes the tests and they pass, he is surprised but satisfied. Joe smiles. Section 9.4.2. Writing mutations with persistent data structures. Theo, shall we move forward and port the add member mutation? Joe, sure. Porting the add member mutation from low-dash to immutable.js only requires you to again replace the underscore with immutable. Let's look at some code. Theo, so for the tests, I convert the JavaScript objects to immutable.js objects with immutable.fromJS. How does this look? Joe, great! Section 9.4.3. Serialization and deserialization. Theo, does immutable.js also support JSON serialization and deserialization? Joe, it supports serialization out of the box. As for deserialization, we need to write our own function. Theo, does immutable.js provide an immutable.stringify function? Joe, that's not necessary because the native JSON.stringify function works with immutable.js objects. Here's another example. Theo, how does JSON.stringify know how to handle an immutable.js collection? Joe, as an OOP developer, you shouldn't be surprised by that. Theo, let me think a minute. Okay, here's my guess. Is that because JSON.stringify calls some method on its argument? Joe, exactly. If the object passed to JSON.stringify has a .toJSON method, it's called by JSON.stringify. Theo, nice. What about JSON deserialization? Joe, that needs to be done in 2 steps. You first convert the JSON string to a JavaScript object, and then to an immutable collection. Theo, something like this piece of code? Joe, exactly. Section 9.4.4, Structural Diff. Theo, so far we have ported pieces of code that dealt with simple data manipulations. I'm curious to see how it goes with complex data manipulations, such as the code that computes the structural diff between 2 maps. Note: Chapter 5 introduces structural diff. Joe, that also works smoothly, but we need to port another 8 functions. Theo, everything looks trivial with one exception, the use of arguments in immutable.union. Joe, in JavaScript, arguments is an implicit array-like object that contains the values of the function arguments. Theo, I see. It's one of those pieces of JavaScript magic. Joe, yep. We need to use arguments because Lodash and immutable.js differ slightly in the signature of the union function. Immutable.set.union receives an array of lists, whereas a Lodash_.union receives several arrays. Theo, makes sense. Let me give it a try. Blowing on his fingers like a seasoned safecracker, first one hand and then the next, Theo begins typing. Once again, Theo is surprised to discover that after replacing the underscore with immutable in listing 9.20, the tests pass with the code in listing 9.21. Joe, what do you think of all this, my friend? Theo, I think that using persistent data collections with a library like immutable.js is much easier than understanding the internals of persistent data structures, but I'm also glad that I know how it works under the hood. After accompanying Joe to the office door, Theo meets Dave. Dave had been peering through the window in Theo's office, looking at the whiteboard, anxious to catch a glimpse of today's topic on DOP. Dave, what did Joe teach you today? Theo, he took me to the university and taught me the foundations of persistent data structures for dealing with immutability at scale. Dave, what's wrong with the structural sharing that I implemented a couple of months ago? Theo, when the number of elements in the collection is big enough, naive structural sharing has performance issues. Dave, I see. Could you tell me more about that? Theo, I'd love to, but my brain isn't functioning properly after this interesting but exhausting day. We'll do it soon, promise. Dave, no worries. Have a nice evening, Theo. Theo, you too, Dave. Summary. It's possible to manually ensure that our data isn't mutated, but it's cumbersome. At scale, naive structural sharing causes a performance hit, both in terms of memory and computation. Naive structural sharing doesn't prevent data structures from being accidentally mutated. Immutable collections are not the same as persistent data structures. Immutable collections don't provide an efficient way to create new versions of the collections. Persistent data structures protect data from mutation. Persistent data structures provide an efficient way to create new versions of the collections. Persistent data structures always preserve the previous version of themselves when they are modified. Persistent data structures represent data internally in such a way that structural sharing scales well, both in terms of memory and computation. When data is immutable, it is safe to share it. Internally, persistence uses a branching factor of 32. In practice, manipulation of persistent data structures is efficient even for collections with 10 billion entries. Due to modern architecture considerations, the performance of updating a persistent list is dominated much more by the depth of the tree than by the number of nodes at each level of the tree. Persistent lists can be manipulated in near constant time. In most languages, third-party libraries provide an implementation of persistent data structures. Paguro collections implement the read-only parts of Java collection interfaces. Paguro collections can be passed to any methods that expect to receive a Java collection without mutating them. Chapter 10. Database Operations. A cloud is a cloud. This chapter covers fetching data from the database, storing data in the database, manipulating data fetched from the database. Traditionally in OOP, we use design patterns and complex layers of objects to structure access to the database. In DOP, we prefer to represent data fetched from the database with generic data collections, namely lists of maps, where fields in the maps correspond to database column values. As we'll see throughout the chapter, the fact that fields inside a map are accessible dynamically via their names allows us to use the same generic code for different data entities. Tip: the best way to manipulate data is to represent data as data. In this chapter, we'll illustrate the application of data-oriented principles when accessing data from a relational database. Basic knowledge of relational database and SQL query syntax, like select, as, where, and inner join, is assumed. This approach can be easily adapted to NoSQL databases. Applications that run on the server usually store data in a database. In DOP, we represent data retrieved from the database the same way we represent any other data in our application, with generic data collections. This leads to reduced system complexity, increased genericity. Section 10.1. Fetching data from the database. Theo and Joe go for a walk in a park near the office. They sit on a bench close to a beautiful lake and gaze at the clouds in the sky. After a couple of minutes of meditative silence, Joe asks Theo, "What do you see?" Theo tells him that this cloud looks to him like a horse, and that one looks like a car. On their way back to the office, Theo asks Joe for an explanation about the clouds. Joe answers with a mysterious smile on his lips. A cloud is a cloud. Theo: so far you've shown me how DOP represents data that lives in the memory of the application. What about data that comes from the outside? Joe: what do you mean by outside? Theo: data that comes from the database. Joe: I'll return the question to you. How do you think that we should represent data that comes from the database in DOP? Theo: as generic data collections, I guess. Joe: exactly. In DOP, we always represent data with generic data collections. Theo: does that mean that we can manipulate data from the database with the same flexibility as we manipulate in-memory data? Joe: definitely. Tip: in DOP, we represent data from the database with generic data collections, and we manipulate it with generic functions. Theo: would you show me how to retrieve book search results when the catalog data is stored in an SQL database? Joe: I'll show you in a moment. First, tell me how you would design the tables that store catalog data. Theo: do you mean the exact table schemas with the information about primary keys and nullability of each and every column? Joe: no, I only need a rough overview of the tables, their columns, and the relationships between the tables. Theo goes to the whiteboard. Figure 10.1 shows the diagram he draws as he explains his thinking to Joe. Theo: I have a books table with 3 columns, title, ISBN, and publication_year. I also have an authors table with 2 columns for ID and name. Here, let me draw these tables on the whiteboard to give you a visual. See tables 10.1 and 10.2. Joe: what about the connection between books and authors? Theo: let's see. A book could be written by multiple authors, and an author could write multiple books. Therefore, I need a many-to-many book_authors table that connects authors and books with 2 columns, book_ISBN and author_ID. Theo once again turns to the whiteboard. He pens the book_authors table 10.3 to show Joe. Joe: great! Let's start with the simplest case. We're going to write code that searches for books matching a title and that returns basic information about the books. By basic information, I mean title, ISBN, and publication year. Theo: what about the book authors? Joe: we'll deal with that later, as it's a bit more complicated. Can you write an SQL query for retrieving books that contain the word habit in their title? Theo: sure. This assignment is quite easy for Theo. First, he jots down the SQL query, then he displays the results in table 10.4. Joe: how would you describe these results as a data collection? Theo: I would say it's a list of maps. Tip: in DOP, accessing data from a NoSQL database is similar to the way we access data from a relational database. Joe: right. Now, can you write the search results as a list of maps? Theo: it doesn't sound too complicated. How about this? Joe: what about the JSON schema for the search results? Theo: it shouldn't be too difficult if you allow me to take a look at the JSON schema cheat sheet you kindly offered me the other day. Joe: of course. The purpose of a gift is to be used by the one who receives it. Theo takes a look at the JSON schema cheat sheet to refresh his memory about the JSON schema syntax. After a few minutes, Theo comes up with a schema for the search results. He certainly is putting Joe's gift to good use. Joe: excellent! Now I'm going to show you how to implement search books in a way that fetches data from the database and returns a JSON string with the results. The cool thing is that we're only going to use generic data collections from the database layer down to the JSON serialization. Theo: will it be similar to the implementation of search books that we wrote when you taught me the basis of DOP? Joe: absolutely. The only difference is that then the state of the system was stored locally, and we queried it with a function like _.filter. Now we use SQL queries to fetch the state from the database. In terms of data representation and manipulation, it's exactly the same. Joe goes to the whiteboard and sketches out the data flow in figure 10.2. Theo studies the diagram. Joe: the data manipulation step in the diagram is implemented via generic functions that manipulate data collections. As our examples get more elaborate, I think you'll see the benefits of being able to manipulate data collections with generic functions. Theo: sounds intriguing. Joe: for the communication with the database, we use a driver that returns a list of maps. In JavaScript, you could use an SQL driver like Node Postgres. Note: see node-postgres.com for more information about this collection of Node.js modules for interfacing with PostgreSQL databases. Theo: and in Java? Joe: in Java, you could use JDBC, Java Database Connectivity, in addition to a small utility function that converts a JDBC result set into a list of maps. If I can use your laptop, I'll show you what I mean. Joe pulls a piece of code from one of his personal GitHub repositories. He then shows the code for the JDBC conversion to Theo, who seems a bit surprised. Tip: converting a JDBC result set into a list of hash maps is quite straightforward. Theo: I expected it to be much more complicated to convert a JDBC result set into a list of hash maps. Joe: it's straightforward because, in a sense, JDBC is data-oriented. Theo: what about the field types? Joe: when we convert a JDBC result set into a list of maps, each value is considered an object. Theo: that's annoying, because it means that in order to access the value, we need to cast it to its type. Joe: yes and no. Look at our book search use case. We pass all the values along without really looking at their type. The concrete value type only matters when we serialize the result into JSON, and that's handled by the JSON serialization library. It's called late binding.